All right. So basically, the mission of packet number 20 is to, of course, give us an idea of material design. And just to give us a little refresher, the idea was is that we were looking at three main different kinds of material properties. Number one, electrical properties, which if we're to design a material and how it behaves, really what we're after is Ohm's law, where basically written in graduate school type of form is the electric field, the current field, and then something that binds the two between them, which is, of course, so-called current, or sorry, the conductivity. So the symbol there, just to make sure that we're not confusing with the stress, I put a little symbol C up there just to realize that it is not simply the stress tensor, although it's also a matrix, but of course it has a completely different meaning. The star here has to do with the fact that it's an effective property relating the averages of the electric field and the averages of the current field, as opposed to a pointwise property, which is relating the pointwise value of the current, the pointwise value of the electric field, and the pointwise value of what the value is at any point inside the body. So the idea is by doing volume averages with the volume averaging operator that simply says, you stick something into here, and that's something I'm going to integrate it over the volume you dictate. The volume is given by this symbol omega, and I'm going to divide by 1 over the volume. Now, one important point here is that oftentimes you'll see this written just simply as the volume V of omega, or you'll sometimes see the symbol absolute value of omega. And the reason that this is sort of a nuanced way of writing what the volume is the fact that the omega is a set of points inside space, and integrating over a set of points, then the measure of it, if you're going to use mathematical lingo, is the volume. And that's actually a scalar number. So usually we either use V, or we say, well, it's like taking the absolute value of a set of points, which of course is the volume. So there was some confusion. A couple of people asked me about exactly what that symbol means and why don't you just use volume. Technically, what you see in the mathematical literature is they try to distinguish between a set of points and the absolute value of a set of points, which is, of course, the volume. So just as a point of reference. Also, in terms of the current field, again, the current, it's given by, of course, amperes per meter squared. That's why it's not simply just I, as it is usually in your undergraduate studies. This is the amperes per unit area. Then you have the electric field, which of course is nothing more than the newtons per charge or coulomb. And then the conductivity, which is given by a variety of different things to balance out what is on the left-hand side and the right-hand side. And of course, in this case, it comes out to be coulomb squared per newtons second meter squared. So again, usually it's given some other units like Siemens and so forth, but all it is really it's a balancing act between the electric field and the current field. Okay? So the idea of the electric field, of course, is it's a invisible type of field that basically measures how big the charge is on a body, the force between the body and another interacting body. So it could be two charged particles, positive and negative, and the force that's between them is given by the electric field divided by Q. This allows this mysterious force to induce this force that we see between two objects. So again, the electric field is somewhat of a made-up quantity. It's really the implicit action of what we feel as force between two charged bodies. By the same token, we can, of course, then write out what the conductivity is relating the current field and the electric field. And again, it's a 3x3 matrix. It's symmetric, positive, definite. In the special case that the current field is isotropic, then we can write it as a single scalar times the identity tensor, and it looks like that. Therefore, in this special case, the current and the electric field are coaxial, meaning they're pointing in the same direction, and the multiplier that tells us how much of the electric field is scaled to be equal to current is given by this, again, conductivity. So it has a very physical feeling when you look at it as a scalar. It simply tells you if you have the electric field, how big of a current will you get? And that, of course, is given by the conductivity. So for example, if it was wood, then wood didn't have any water in it because of course water conducts electricity, but let's say a dry piece of wood, it may have a strong electric field inside of it, but it may induce no current simply because the conductivity is nearly zero. So again, that's, just keep that in mind. It's similar to stress and strain in some sense of how we do that, but we'll talk a little bit more about that. So when we consider wires, as we have in undergraduate studies, the current then is really just one-dimensional, and you get all of the lovely things that you see in your electrical engineering classes. For example, Thevenin's theorem, Ohm's law, all of the circuit analysis where people are doing all kinds of stuff for flow of electricity. These are just simply nothing more than averaged quantities that give you just a scalar one-dimensional flow of electricity through some kind of wiring or some kind of a system. And that, of course, means simply that the current field is just going to be given to be zero in the transaxial direction, and then just simply along the axis of the wire is just a single number. There is also a relationship between the voltage. The voltage is this quantity that simply says if I take the gradient of it, I can then extract that back out the electric field. That's very important sometimes when we're thinking about voltage potential, because of course, if you have a electric car or you have some kind of a battery, the voltage is important because it also allows you to give you a quantity that you can determine how much usable energy is available for use for the vehicle when it's being produced, or for any other object as well. So in electrical engineering, the voltage is something that people care about a lot because it allows us also to calibrate devices. The thermal fields, very similar again. We have basically the gradient of the temperature, which is given by theta. We have something called the conductivity. There's a minus sign since hot goes to cold. We have the flow of thermal energy. And then if we average both sides of these things here, the average of the gradient of the temperature, the average of the flow of heat, then we get this effective property, which is a so-called effective conductivity. And then in this case, it's going to be the thermal flux, which is going to be equal to the watts per meter squared or joules per second per meter squared. Theta is the temperature, usually given in Kelvin or in Celsius. Rarely is it given in Fahrenheit. Then finally, the conductivity, or the thermal conductivity, is just going to simply be watts per degree Kelvin per meter. So once we take the gradient of the temperature's gradient is a vector. And if we relate the vector to the vector of the heat flow, so Q, of course, is Q1, Q2, Q3, it is a vector. The thermal field, or the gradient of it, is also a vector. So what relates the two vectors to each other is a matrix of constants, and we refer to those matrix of constants as the thermal conductivity. So in the special case, however, when the thermal conductivity is a scalar, we can write it as K times I, and therefore we get just simply the simple relationship that says Q is equal to minus K times the gradient of the temperature. And of course, this is the number we just usually refer to as the conductivity or the thermal conductivity of the materials. So it's nearly identical to the concepts of current and electric field, except that the conductivity K takes the place of the electrical conductivity sigma C for electrical flow. Finally, the one that we're probably most familiar with by now is the so-called Hookean type of law. So we're taking a very simple relationship that simply says you have the strain, you have the stress, and the thing that relates the two between them is the so-called elasticity tensor. And of course, in 1D, that's just simply the Young's modulus of the material. We then take the volumetric average of both sides, and the thing that binds the two together, this averaged vector and this average vector, is the so-called effective mechanical strength or the mechanical stiffness of the material. So again, the star indicates that it is a overall property as well. So again, those are the three big ones that we consider. And so at this point, we want to actually now look at some problems that we can solve and see what is this stuff actually good for. So the whole idea of volume averaging, effective properties, let's see what exactly we're getting into. So here's the basic idea, which I'll first go over in a very broad sense, and then we'll come back and drill down starting in packet number 20 on page number 6. So the idea is for example, let's suppose we were taking a PG&E transmission line, and I wanted to determine the overall properties of some kind of new piece of wire between different transformers or inverters or things of that sort. So I'm going to take a piece of material, I'm going to design it, I'm going to take a wire, I'm going to dope it with all kinds of particles inside, and I'm going to ask myself the following question. If I take the matrix volume of the material, of just the stuff that's without the dopants, so the dopants, of course, could be of some value depending upon what I want to do. So I want to use them sparingly. So for example, it could be that the line is made out of a low-grade copper, and then I put some pretty high conductivity particles inside to enhance the properties of the copper. It could be something along those lines. So we're just going to consider two phases. We have a phase that's a bulk phase where it's relatively cheap and easy. So we're going to put some material into deployment. That's, of course, one of these sections here, but we're going to enhance it with these particles, which are given by that. So we're going to call the particles with subscript P, and we're going to call the rest of the material the matrix with subscript M. So if I take the total volume that is of this cylindrical element here, it's going to equal to pi r squared times the length of that piece or specimen, which is the total volume of the material. So that is the total volume of the material. If I subtract away the volume of the particles, I get then what's remaining is the volume of the matrix, and vice versa. If I subtracted away the matrix material, I would have gotten the volume fraction of the particles. So let's consider spherical particles just to make this example somewhat easy. So we know that 4/3 pi r cubed times n is equal to the total volume of the particles, where n is the number of particles inside the section of material. So that's something we're going to determine in a second. How many particles are we talking about here? Is it 100? Is it 100,000? Is it a million? Well, we're going to make a ballpark estimate of exactly what's going on. So the total volume V is given by the volume of the matrix plus the volume of the particles. Therefore, as we know, if we divide by the volume on both sides, as we did last week in class, we get this relationship that simply says 1 is equal to the volume fraction of the matrix and volume fraction of the particles. The volume fraction of the particles is given by each one of the individual particles divided by the total volume, and there are n of those inside. Okay. The idea then is that if we have the same thing for the volume fraction of the matrix, it's just going to be 1 minus that quantity, which is here, and that gives us then the volume fraction of the matrix. So the first basic questions are the following. How does the property of the mixture change as a function of Vp? So if, for example, if this wire had been that low-grade copper that was here before, and I start to dope this and add stuff, how are the properties going to change? Well, there's a couple of ones we care about, right? If we were thinking about some kind of a structure where we're going to make some kind of a transformer, so let's put a wire here, and let me put it at the suspension. Then I have now some kind of wire here in a transformer, and I'm doing it in between two different sections. So let me draw it like this. So that is a pretty cheap and easy way, simple model for the transmission. So I'm trying to design the thing here that's shown dark. So first of all, I'd probably want this thing to be pretty stiff because I don't want it to sag. If it were starting to sag, that might be a problem because when the wind starts to become relatively strong, we're going to start to get vibrations. So clearly I want this thing to be relatively taut and stiff. Number two, I'd like it to actually do its job, which is conduct the electricity. So I want to also get the properties of the conductivity. And I don't want this thing to get really hot. I mean, that's a big deal, right? I mean, if the stuff gets really hot, it's going to start a fire. So there are all kinds of properties, but the three big ones that I would care about in this kind of a system is, number one, I need to get the effective elastic properties correct. I need to get the effective conductive properties correctly, and I need to get also the effective thermal properties correctly. Now, depending upon, if I look at the curves, increasing the volume fraction of the particles I could add, it might be that the curve that is dictating how the properties change or the stiffness change might behave like this. The conductivity might behave in a slightly different manner. The thermal conductivity might behave in a completely different fashion. So what I need to do is I need to figure out what are the formulas or what are the relationships that tell me as I start to dope and add material to this thing, what is it going to actually deliver for me? Okay, so the objective first is, number one, let's see how many particles are actually inside of this thing. So if I looked at a typical wire, let's say with radius 1 centimeter. So pretty thick wire, but that's of course pretty standard for something that might be used for high conductivity lines. And I go through the calculations, which I would ask you to do. In the section of roughly only 1/10 of a meter, so basically 10 centimeters long, what we find out is roughly there's 1 billion particles inside. So if we grind up particles and we put them into the mix and we compute how many particles are inside, what you find out is there's about 1 billion particles. Now, the first question is going to ask, well, how do we compute something with 1 billion particles? The answer is we don't. I mean, that one is just simply computationally unwarranted. And it's also rather expensive and completely, a waste of computational resources. So the idea is we'd like to figure out if we have one of these wires with all of this crazy material inside, and there's 1 billion particles in this section, could I replace this section with some kind of homogenized effective property, like I was showing you here, effective elastic, effective electrically conductivity, and electrical thermal conductivity? And the answer, of course, is obviously it's a loaded question. The answer is clearly yes, you can do this. So the important quantities that we're after in this case are going to be, number one, we want to get the average current and average electric field, and we want to get the effective electrical conductivity, the effective thermal flow, the effective gradient of the temperature, and then again, the effective thermal conductivity, then the effective elastic properties relating the average stress and the average strain. So the first and simplest approximation for this to figure out exactly what are these properties, let's look at the case, for example, on the electrical conductivity. Now, as you may recall from last week, we went through an analysis of springs in parallel, springs in series, and not to belabor that issue, essentially what we found out is that if we take the rule of mixtures, it is going to always be an upper bound of the electrical conductivity's effective property. And if we take the 1 over the effective properties and invert it, we get also the lower bound of the electrical property. So we're going to call these two quantities here the upper bound, which is sigma c star plus, and then we're going to call the lower bound sigma c star minus. So the idea there is that we're going to have an effective property which we don't know, but we can actually determine that there are bounds above and below sigma star c plus and sigma star c minus. These two quantities here are given by those two formulas. The first formula, again, is the volume fraction of the first type of material multiplied times the conductivity of the first material. And again, then we invert that, plus the volume fraction of the second material times the conductivity of the second material, again, inverted, and then we invert that whole thing. That's what the lower bound is. That's sometimes called the harmonic average. And as I indicated last week in class, in 1952, Mr. Rodney Hill proved that that was in fact a lower bound to the actual effective property, which is shown here. By the same token, the rule of mixtures, which is the easier one, basically says that if you just take the volume fraction of the first phase, so call that sigma C1, plus the volume fraction of the second phase, which is sigma C2, those two quantities added together always give you an upper bound of what the property can be. Now, if we plot those properties, as I'm showing you here on page number 10, what we find out is that we have the upper bound is this curve on the top, the lower bound is the curve on the bottom. And so depending upon what happens between here, this gives me an upper and a lower estimate at any volume fraction for what the worst that property could be and what the best that property could be. Now, what we usually do is we average those properties. So for example, as you'll see here, we basically take the volume, we take sigma C star, which is approximately equal to the average of the properties. So let's see how we would write it out. Let me write it as phi times sigma C star plus. So we basically take that quantity there. Then we have this equal to, and this should be, of course, an equal here, plus 1 minus phi multiplied times sigma C star minus. And when we take phi, phi is going to be a parameter that lives between 0 and 1. If phi is equal to 1, so this is something we're going to adjust, it means that this term is going to be taken out of the system, and it's only going to be equal to the upper bound. So if we pick phi equal to 1, we're basically saying that we have an estimate that is close to the upper bound. If we take phi equal to 0, we then have this thing taken out of the system, and we have simply a 1 minus 0 here, and that gives us the lower bound. If we take phi equal to a half, we basically get the average of the two bounds. So 0 means all lower bound, 1 means all upper bound, half means an average of the two. So the first question is well, okay, fine, that's wonderful, but how do we get this phi? That's usually actually experimentally calibrated. People will go do an experiment, they'll take a piece of material, they'll see how close the upper or the lower bound is for certain values of the volume fraction, and then they'll basically pin that down, and they'll simply use that value of phi for all of the ensuing calculations. So it's almost like a calibration constant that tells you how much of the upper and lower bound are there. Now, the problem with this estimate is depending upon how wide these bounds are, so they can be relatively wide, just simply figuring out what the average is or what this value of phi is may give a little bit of inaccurate results. Now, 1962 or so, Hashine and Strickman, they said, well, we could possibly improve upon this. It's certainly rational to take some kind of convex combination or average using these phis, but wouldn't it be nice if the lower bound and the upper bound were closer to each other? That way you would get tighter estimates. So what they did is they came and went through an extremely complex analysis. You can see it in the reader. But basically in 1962, they were able to compute the following. So they found out that the sigma c star is bounded above y, and I'm just going to simply point to sigma c star Hashine-Strickman plus and sigma c star Hashine-Strickman minus, and we're going to say C page 10. So on page 10, basically this is the sigma c star plus of the Hashine-Strickman bounds, and this is the sigma c star for the Hashine-Strickman lower bounds. Now, the importance of these things is that what we do is we then take this estimate, and we again repeat the same thing. We simply take the phi times the upper bound and 1 minus phi times the lower bound, and then we're able to compute the overall property of sigma c star. That's pretty much the state of the art in terms of what people do, unless they're going to go through a much more intensive computational experimental analysis. So day in and day out, you'll find people at Apple or at people at Siemens or Bosch or any of the companies that are dealing with pretty complex materials. This is pretty much what they're going to be using. They're going to take that kind of an estimate. They're going to take the upper and lower bounds, and then they're basically going to take the average and 1 minus phi and phi here, and they're basically then going to produce some kind of value for the estimate. Now, the nice thing about this is that we can use this in an optimization technique to basically apply our machine learning and genetic algorithms. So the idea is that this estimate, let's write it out as sigma c star approximate. So I'll put a little a here, which is phi times sigma c star Hashine-Strickman plus 1 minus phi times sigma c star Hashine-Strickman minus, that this thing is just one ginormous function of what? The volume fraction of the first phase, the volume fraction of the second phase, the conductivity of the first phase, the conductivity of the second phase, and so forth. There could be many different possible parameters, right? So the idea then, of course, is that we know a couple of things. The volume fraction of 1 plus the volume fraction of 2 is equal to 1. So if I'm looking at a two-phase material and I call, let's say, the particles, I'll call those number 2. So call that phase number 2, and I'll call this phase number 1. It turns out that if I take 1 plus that, it actually equals to 1. So one of these variables is actually redundant. So the upshot here is I really can write this as F is equal to a function of V1 or V2, sigma 1 star and sigma 2 star. Sorry, sigma 2, sorry. So the main idea here then is we have three parameters. We have the conductivity of the second phase, we have the conductivity of the first phase, and we have how much of the second phase we added. So this gives us immediately something we can optimize. So we have our tool that we can come along and clobber things with. And the tool that we're going to clobber things with are we want to design the material. So the idea is that we have a target response that we want. So let's call that sigma C star desired. And then I also have what I generated, my approximate solution. My approximate solution is sigma C star approximate. And I want to get the approximate solution as close as possible to the design solution. Well, that's pretty simple then. So the cost function now becomes, which is a function of V2C, sigma 1C, sigma 2C is equal to the absolute value of sigma C star desired minus sigma C star approximate divided by sigma C star approximate. Okay. Now, you could immediately take your genetic algorithm or your machine learning algorithm, switch out whichever one of the assignments you had in there, and immediately put this as the cost function, where the only thing you have to change out is the approximations that give you the values of sigma C star A. And that again is given by taking the upper bound, the lower bound, and then combining them in the following fashion. That's in fact exactly what this relationship is right here. So the point of this exercise is that we're able then to design the current field or the conductivity in the following fashion. Now, oftentimes, and this is where your assignment comes in, we're not just interested in, of course, the electrical properties alone. What we would also like to do is design the conductivity, the thermal conductivity. So let's call that sigma, or sorry, K star desired. And then we'd also like to have the electric field, or sorry, the elasticity also desired. Now, I did the first third for you. I set it up. What I would like you to do is to read through the notes to do the second ones, which the second ones are basically here starting on, let's see, just 1 second. Yeah, for the mechanical properties here, given same thing using now the elasticity and the elastic coefficients, we follow exactly the same thing for the conductivity. And then also for the thermal conductivity, the same exact approach. Now, you're seeing a lot of other formulas. And so what I would like to do is to first go on a macroscopic scale. I want to design something that designs number one, sigma C, K, and elasticity. And this thing, I'm going to set it up as a cost function where I'm going to put a weight and I'm going to design the effective desired electrical property and the effective approximate value there. And I'm going to divide it and normalize it by sigma C star desired. That's the one we just did. But I'm going to put a weight here that tells me how important it is to get this value here as accurate as possible, because what I'm going to do next is I'm going to add W2 times the thermal conductivity that I would like it to be minus the thermal conductivity of the average or approximation divided by sigma star of the desired, and again having that value there. So depending upon how I pick W, I could make the bias more towards designing electrical properties or the bias more towards designing the thermal properties. Now, there's one other field that we would like, and that's basically also the elastic fields. So we take then basically the norm of the desired effective elasticity. So be careful, that's a tensor. So I'm going to put two lines underneath here to indicate that this is not just simply an absolute value. I take the difference between that and the effective properties that I have an approximation for, which again are given by those formulas, which you're going to derive as part of your homework assignment. And then I also have the elasticity of the desired properties here, and I take those norms as well. So the main point here is that simultaneously, I can design the effective electrical properties, the effective thermal properties, and then also the effective elastic properties all simultaneously. And that's the beauty of this. It really works. I have to say I used, when I first derived these almost 15 years ago, I used them in a number of corporate ventures with the Siemens Corporation, and it really does design the material properties as advertised. So the main point is that when we do all of this type of an analysis, so as you'll see as part of your homework assignment, I'm going to ask you to derive these, you basically can get the entire formula, which I'll show you here, which basically says I can design simultaneously the electric field, the thermal fields, and the mechanical fields simultaneously. Now, what are all of the parameters that are in the system? This is worth reviewing. Number one, we have the conductivity of the first phase, the conductivity of the second phase, the thermal conductivity of the first phase, the thermal conductivity of the second phase, the elastic coefficients. So in this case, if I assume it's isotropic, the bulk modulus of the first phase, the shear modulus of the first phase, the bulk modulus of the second phase, the bulk modulus, or sorry, the shear modulus of the second phase, and then finally, how much of the stuff do I add in there? So as you can see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters, and it would be very difficult to figure out exactly how to design all 9 without some kind of automated technique. And that's, of course, where our machine learning algorithms come in. So that was what I wanted to deliver for us today. I realize it's a lot of information, but there are a couple of things that I want to draw to your attention now when we start at the very beginning. Okay, so what we refer to this quantity here, this entire 3-piece thing, this is the so-called macroscopic macro design. Now, part of the problem with this is these are only looking at the overall averaged properties for the entire structure as a whole. What we would like to also add is what we sometimes refer to as microscopic constraints. Okay. Now, microscopic constraints, that's going to be an important topic, and that starts also basically on page number 12. So I don't want to dive right into that because I want to give you time to read over this packet carefully. So what I would like you to do is to read packet 20 in entirety, and also the corresponding chapter in the notes. We'll go through the microscopic aspects of this to add the microscopic design constraints. We'll put all of them together, and then we'll basically have set up assignment number 5. Brian, is there anything that you want to add to this before we kind of stop and maybe have some Q&A?
Not at the moment.
Okay. So you'll find this assignment is very clean. It's rather elegant. It takes a little bit of time just to get used to putting all of the terms together, but Brian is going to provide you with a variety of templates, but the payoff is significant. You can really design a variety of exotic materials in an automated way. And of course, this has taken on a life of its own in industry. People use this now in a variety of different areas. For example, the Material Genome Initiative, which is, a fancy word for basically saying, you tell me the property you want, and I will dial up exactly how you can combine different materials to deliver the property that you seek. So the problem, however, in all of these kinds of analyses is that when you look at a piece of material, so let's suppose we look under the microscope and we look at some kind of a structure, anytime we start to load it up, what happens is the material has different load sharing techniques. What that means are capabilities, meaning that the particles take some part of the load, and that load could be a thermal load, elastic load, electrical load, and the matrix takes on a load of material now, or load in response. Now, depending upon one or the other materials, one part of the material might fail depending upon how much of the load it has to take. You can imagine if you think about your undergraduate days in strength of materials, and you may have had seen problems in composites or steel design, where you pull on a piece of material and you ask yourself how much of the stress is carried by the steel, shown here, and how much of the stress is carried by the surrounding concrete or things of that sort. And you go through a simple analysis and you find out how much of the load is shared by the steel, how much of the load is shared by the concrete. That's what we do in so-called microscopic designs. We do this in a much more elegant way, and we do this for the electrical fields, the thermal fields, the mechanical fields, and we construct so-called load sharing algorithms or load sharing expressions. Now, the main point that is important here is that when we design a material that is a so-called macro micro design, basically what we do is we take the macroscopic part, which is the one that is attending to things like sigma C star, kappa star, E star, and then we add also a so-called microscopic constraint, and the microscopic constraint takes into account how much of the load is actually carried by each of the different phases. So the different phases are basically going to be represented, and how much load they carry is by this term here, but I'll save that for Thursday. Now, after we're done with this section, we'll give you plenty of time to work on it. It's a relatively clean one, but keep in mind that your entire machine learning and genetic algorithm framework is going to give you the ability to switch out whatever you want in these kinds of design processes. So for example, we're still going to have the process of taking a design vector, but in this case, our design vector. So if we think about here at the very last page of this, the design vector in this case is going to be a 9x1 design vector, and it's basically going to be all of the materials and the volume fractions of the material. We input this into our simulator. Our simulator is going to be that average expression of phi times this plus 1 minus phi times this, complicated formulas, but we'll call that the simulator. And out pops here is basically the value of the micro and the macro response of the system. And then we keep readjusting the lambdas over and over again, constantly using our estimates to drive the process, checking the performance, and then feeding it back over and over again. Tailor-made for the genetic algorithm and all of its good works. So we'll try to wrap this all up on Thursday. But if there are any questions, I'm going to stop here for the time being, because I realize this is a lot of information to kind of load in. So it's not like a chalkboard lecture where, I mean, I think this would have normally taken me probably 2 lectures. And of course, by going through the notes and like this, I don't want to overburden you, but I'm happy to answer questions, or we can save them for on Thursday. So the floor is open if someone would like to ask something. Ron, oh, sorry, go ahead, Daniel.
So this might be a bit of a out of the reach of this course, but when it comes to taking the norm of the elasticity tensor, when you had your cost function, obviously so far we've been assuming the material is isotropic, hence it has a matrix, a 6x6 matrix representation.
Excellent question. Yeah.
But
yes, so what
in
I
this
mean
case
by
is
that,
how will we calculate the norm?
Yeah. So what I mean by that symbol, and I'm being a little bit cavalier there. I mean, let's see. So design, let's call it approximate, and then this design really exactly what I mean. There is that I meant simply that you take the bulk modulus of the material minus the bulk modulus design approximate plus the shear modulus of the desired minus the shear modulus of the approximate. And then we basically take the absolute value. So I'm assuming it's isotropic. Now, if I didn't assume it's isotropic, literally what I would do is I would take the entire matrix of coefficients, E, I, J, K, L, minus EIJKL star of the desired. So all of the 6x6 matrix of coefficients that are inside of here. And then I would also take sigma C star approximate, and I would literally take the absolute value of all of them and sum over all of the I, the J's, and the K's. So basically I would go through every single coefficient here, and I would take every single coefficient here, and I would take the difference between here and here, here and here, here and here, add them all up, and that would be the symbol of that. Now, in the isotropic case, it becomes somewhat simpler because really we know that only two of the parameters in here are linearly independent. So basically kappa and mu. So there, in that case, I simply only have to take the difference between the bulk modulus and its other bulk modulus and the shear modulus and the shear modulus here. But if I were to do it rigorously for an anisotropic material, I would have to subtract away all of the coefficients in each of these matrices, sum up the difference between the two. Depending upon the norm you like, you could put squared, but typically it's just going to be the absolute value. And I would subtract and add up all of the differences together.
Awesome. Thank you for the response.
Sure. Any other questions? So Brian, I do have a question just in general logistically. When is assignment number, I guess this would be assignment number 5, is that correct?
This one will be in assignment number 6. So assignment number 5 is the laser, the three-dimensional laser problem.
So assignment number 6 then is due, when is that, like at the end of the semester? I mean, I think we need to give ample time. I don't want to overload everybody, but is there a due date on that?
Yeah, so we can talk about that real quick. So the assignment 5 is due next week on Tuesday, the 13th, so a week from today.
Okay.
And then I mean, like if that one's causing trouble, maybe we can push it back to like Thursday.
Okay.
But then I was thinking of having this homework 6 due on the 22nd, the Thursday.
Okay.
Or the 27th.
I think the 27th would be better, but
okay.
Let me ask the class, at least the persons that are online, how are you guys doing with assignments in terms of pace? Do you need more time, do you think, for assignment number 6? I guess that's a silly question. Everybody will always say I need more time. But in general, is the pace reasonable, or should we kind of slow it down a bit?
I think the pace has been overall reasonable.
Okay.
So I think the big thing that I'm trying to do is make sure that it's reasonable for the very last assignment. So that would be the COF simulation.
Okay.
I don't think that one will be too difficult, as most of the basically all the dynamics we did in homework 1. So even like the strategy of handling the particles in the air from the robot arm it's very similar to how to handle the particles coming out of your mouth when you cough.
Yeah, I think what you'll find is assignment number 7 is a piece of cake. I mean, it's fairly easy. This one also, once you get the hang of it, it's just some formulas that you put in for your genetic algorithm. They're also not very difficult, this assignment, but it's intellectually, takes a little bit of time getting used to. Laser one is tough. I mean, that one's, finite differences and stuff. So I think, Brian, if we could give everybody a little bit more time on that and make the last 2 assignments due at the end of the semester to give people breathing room, I think that would be the best.
Yeah, that works. So maybe we can push the due date back for homework 5 until April 15th.
Yeah, that's
at Thursday. So a week and 2 days.
Does that seem reasonable to everybody? You're masters of your own destiny. Someone say something. Is that a yes?
Looks like Daniel's giving a thumbs up.
All right, everybody.
That's good.
As long as you have more time, it's a graduate class, so the objective is to learn. So, I mean, I don't want to pressure you overly. I mean, I realize it's a tough situation for everybody. So let's assume that the assignments, the last 2, are due at the end to give you some time. Then the assignment number 5 is on the 15th. And I think you'll really like what's coming towards the end. It's kind of a fun thing on a sort of a sad topic with manufacturing and, COVID-19 and infections and stuff, but it's intellectually enriching. I sent in the chat, by the way, that at the very beginning of class, you'll see that there's in the chat, there is this one thing that is basically talking about the modeling of these kinds of things. Take a look at it because it really is quite relevant. I mean, manufacturing clean room operation, I don't think there could be anything less important in the Bay Area. The Bay Area lives and dies by semiconductors. That's of course why it's called Silicon Valley. It would be a good idea to read what's in the chat first, just to kind of get an idea of what's going on. And then we can go do a deep dive after Thursday, and maybe we'll even start getting to it on Thursday. But again, the so-called macro-micro design of materials is an important one. And in fact, that's what most of the people are doing in clean rooms is, in fact, they are designing materials. So this is a natural extension to the actual operation of exactly what is going on. So I'll save that for Thursday, and we have plenty of time. I figured that by roughly around April 20th, we'll be done with all of the bulk of the material that I wanted to cover. And then we'll basically do a deep dive and a thorough review starting from the very beginning and go through every nook and cranny and make sure we've understood everything. So at least you've seen it twice. So I know sometimes it doesn't get through the first time, but hopefully by the second time of seeing everything, and if you're very organized with the packets, and I think they're very sequential, but I'm biased because I wrote the packets, but I hope that the packets are somewhat logical. And then what we can do is we can go through the entire system again and prepare for the final. So does that sound like a good plan? Sounds like a good plan to me.
Excellent plan.
All right. Well, have a good day, and I'll see you all on Thursday.